lower Q or cascaded L networks. Now, if you are looking out for a wideband match, unlike the pi or T networks, you can cascade the L sections. For example, over here, you have this first L section of inductor and capacitor. Let's call this L1, C1, and then you have cascaded another L section. Okay, same two element L network, same topology. So L2, C2. So again, you have two passive reactive elements, but you are cascading two L sections over here. Okay, so let's call this the first section. This is your second section. So this is a double L network for lower Q or wider bandwidth. This could be the other way around as well. It doesn't matter if you have an inductor or a capacitor over here, and then you have a capacitor, inductor. So it could be a combination. So it's etc. It could be all inductors. It could be all capacitors. So you have those combinations. You can make those combinations with the non-resistive or reactive elements. So what happens is that unlike pi or T networks, in a cascaded over here in double L network, which is shown below, the first L network transforms to an impedance value that is between the source and load impedance. So we have the source impedance, which is in most of the cases different from the load impedance at a certain frequency. For the purpose of matching, we recall that RS, if this is real, if RS and RL are real, then RS should be equal to RL for maximum power transfer. Okay, if they are complex, then it should be the conjugate match of the it should be in conjugate matching. So RS should be the conjugate of RL. Okay, to obtain the maximum power transfer. Now you see, if RS and RL are not equal, okay, and if you recall in our previous discussion on L networks, the basics are that you keep the shunt element. This is your shunt reactive element. Okay, it could be capacitive, it could be inductive in either case. This comes across with the higher source impedance. So let's say RS in this case is 1000. Okay, and suppose you have to match this to a load resistance of, call it 50 ohms. Okay, if it were to be a single L section, forget about the second L section, your shunt reactive element is supposed to come across 1000 ohms, okay, which is the higher. And then the series reactive element, L or C, comes across the 50 ohms. So over here, the same thing occurs. You see, this over here, you have an impedance transformation at the center. Let's call this Z center. Okay, let's call this Z center. So since the shunt reactive element is across, or it comes in shunt with the higher impedance of the circuit, the first L section, in series with the inductance, ZC is supposed to be less than whatever the center impedance is transformed to at this point in the circuit, will be less than RS 1000. Okay, and for the second stage, since C2 is again, this reactive element is again in parallel or in shunt with ZC. Okay, so this ZC is supposed to be greater than RL, because in series with L2 you have RL. So ZC is supposed to be greater than RL. Okay, so your center impedance for a double L network, like we are looking at this topology or this topology, So the first L network is transforming to an impedance that is in between source and the load impedance. Okay, so that's the point. So if you have to design a double L network, then your center impedance will be a transformation of the impedance. The value of it will lie between the load and the source resistance. Okay, it will be less than the source resistance if that is higher than the load resistance, or it could be the other way around. Okay, if the load is 1000, this is 50, then it's the other way around. So ZC will be greater than RS and less than RL. Okay, so somewhere in between your load and source resistance, given the topology of the configuration of the cascaded L sections. Okay, the idea is that your shunt reactive element is in parallel with the higher impedance. So with the series, you're going to have a lower impedance. Okay, so lower than RS in this case, and again higher than the load resistance because this is again shunt. Okay, so that's the idea. So the second stage takes it the rest of the way. The process can of course be done in a smaller steps with any number of cascaded networks. You can have multiple cascading. For example, this is a single L section, two element L section matching network, matching the source resistance with the load resistance, unequal source and load resistances. Similarly, you can have a double L network that we've discussed before with a certain Z center, which is in between RS and RL. If RS is greater than, call it RS greater than RL, so that should be the case. Okay, so if this is for RS being the higher impedance in the network, because the only resistive elements are the source and load resistances. So in this case, if that is the case, then your center transform impedance is a value that is in between. Well, I think I've written this incorrectly. This is supposed to be less than RS and greater than RL. Okay, just like what we have discussed before. So if you can follow the same steps. Okay, for example, over here you'll have two in three section or three L sections or six element matching networks. If you are cascading them, then you have two Z center impedances. Let's call this Z1. Then you have another Z2. Okay, so let's say again RS is greater than the load resistance, then your Z1 of course will be greater than will be less than RS, that is for sure, and it will be greater than Z2. Okay, it will be greater than Z2 because this network, the first network, is looking at so the 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 first network is transforming the second network. This is your second network, that is your third network. Okay, and this is the first network. So the second and third are being transformed to an impedance called Z1, and Z1 is supposed to be less than RS. Okay, similarly then Z1 is supposed to be greater than Z2. Okay, why? Because Z2 over here, Z2 is in series with L2. Okay, and Z1 is over here. So Z1 is across the shunt reactive element, so it is supposed to be higher than Z2. Okay, so that's the idea. Z1 is greater than Z2. So you keep on repeating the same steps if you have more cascaded sections. So again, Z2 will of course be greater than RL. Is greater than RL. Okay, it's not very nice. So RL Z2 is greater than RL, but it's less than Z1, which is basically the same situation that we have earlier. So Z1 is greater than Z2. Okay. So you have two for three sections. You have two center impedances. Similarly, for let's say n section n cascaded L networks, you have n minus one center impedances, and you can set this values of the center impedances accordingly. Okay, depending on which side the shunt reactive element is. So which side is the higher source resistance, which is higher, or the load resistance. So accordingly, you're going to set your center impedances. Okay, so if you recall the Q method of designing in the first few lectures of L matching sections that we have discussed before, if you want to follow those discussion, just click on the links that I've provided in the description. Just visit that. So the Q method that we have is for these L matching networks. You consider the high and low and impedances. Okay, find the Q, and then find the corresponding values of the reactive elements at the given design frequency. So in this case, let's say the design frequency is 1.5 megahertz, and you have a load that is 50 ohms, which is supposed to be matched to a source impedance of 1000 ohms. Okay, so you find the Q of the high impedance is 1000, the low is 50, and that's what you get is 4.36. And you use those design equations as you've done before. So X parallel is 229.36, and at 1.5 megahertz in the parallel element is capacitive. So you have a capacitive reactance of 462, and then the series is inductive. So at 1.5 megahertz you have an inductance of 23.12 microhenries, and if this red you fill up this table for the single L section, you have the matching, the maximum power transfer at the design frequency, that's 1.5 megahertz. You can see that there is no power being transferred at the high frequencies, and we have talked before. The reason for this is because you see at high frequencies what's going on over here is that this capacitor is being shorted out, okay, and the inductor becomes open. Okay, so basically there is no power that's being transferred. All the power is going to the ground. Okay, so there is no power that is being transferred to the load resistance over here. Over here at the DC, this circuit is basically the inductor is short at DC, capacitor is open, so it's just 1000 against 50 ohms. Okay, so there is a mismatch over here. There's no match, so you end up in the lower power that is being transferred around DC or low frequencies. At design frequency, well, yes, the source, actually this LC reactive element transforms this 50 so that the load and the source impedance, they become equal. So at this frequency, what is going on is that RL is equal to RS, or RS is equal to RL. So basically the source is looking upon at the same load resistor, so the maximum power is being transferred. That's your power. Okay, these simulations are done in advanced design systems. You can see the logo over here. A linear circuit element is set up and an AC analysis is run, because you have it's a linear circuit. You don't have any non-linear circuit elements. So and the power is extracted at this node. That's your V out or P out, whatever it is. So V out square divided by 50 is your P out. So that's the magnitude of P out over here. Continuing the same method. Okay, now for example here you have two L sections. Okay, and this is two sections, so we have just one center impedance, which I've set it to be equal to 200. Okay, this 200 is in between 1050 as we've discussed before. So over here my Z is 200. Okay, so what this means is that your second L section, this is your second L section, this is your first L section. So second L section with 200 on the primary side, on the first L section side, you have this 200 source impedance, okay, which you use this for the calculation of the second L. So 200 is the higher source resistance. So with this 200, 50 is the low resistance. Okay, the entire thing, this is transformed to 200 ohms. Okay, 50 matches to 200, and then this 200 is going to match to 1000 via the first network using L1 and C1. Okay, so the second L section is matched to 200, and then this 200 is matched to 1000. Okay, so that's your cascaded, double cascaded L section network. Okay, so for the first stage, you separately find out what the Qs are using R. So R high is 1000 over here. Okay, R low is 200 on the other side. So that's your Q, and then you find those X parallel, the reactive. So parallel is capacitive reactance, series is your inductive reactance. So you find the values of those inductor and capacitance for the circuit elements at 1.5 megahertz. That's your design frequency at which you wish to match or to maximize the power transfer over here, which you can see. So you do the same for you carry out the same procedure for the second L stage. This is your second L stage. And then your high impedance is 200, along which there is a shunt capacitive element, reactive element, and 50 is the low resistance. So you find the Q, and then from that Q you find out the parallel and reactive series elements. Okay, at 1.5 megahertz, what are the values? So I've calculated them. You can follow this. You can see for their correctness if you are interested to check out these values. So at 1.5 megahertz, what happens is that if you follow this, so this double L network is in blue, and well, this blue curve is basically uh, your frequency. It's the frequency response of the power that you are obtaining at the load side. Well, it does shows that at the desired frequency, the maximum power is transferred, but then there is a certain plateau region over here. Okay, so you can see that the Q of your double L or 2L section, this is your Q2L, and the red one was for Q1L. Okay, so basically these red values, these these red values are for this curve. Okay, so Q2L is less than Q1L. Okay, because the bandwidth of the match is much wider in the double L network. Okay, so the Q is smaller. The Q is smaller. That's a thing to observe over here. And then again, you can see that at high frequency you don't have any power that's being transferred. Why? Because inductors are open, capacitors are short, so there is no. At low or DC, near DC, low frequencies, basically you have 1000 across 50. Okay, because those inductors are short and capacitors are open, so the capacitor they won't matter, and the inductors are short, so they're at DC in the inductance. You don't have any inductive reactance, so there's a mismatch. But on design frequency, the match of the bandwidth of the match becomes wider. Okay, so the Q falls. So the Q is falling. Okay, as you're increasing the L sections, as you're increasing the number of L sections, so as L sections are growing, number of L sections are growing, basically your Q or the quality factor is decreasing. So that's the story. And you can see this for three three L sections cascaded. You will have Z center impedance is Z1, you will have Z2, okay, and you can see that these two values are again in between the 1000 and 50. So for example, over here, you are going to select this to 500, okay, which is less than 1000. But again, it's greater than 50, okay, because why? Because this 500 is going to appear at this Z1 is, if this Z1 is 500, and this is supposed to be greater than ZL2. So ZL1 is basically greater than ZL2. Okay, it has to be, because the your shunt capacitive elements are in parallel or coming across Z1 and Z2. Okay, so these are higher impedances as compared to, for example, Z2 is greater than 50. Okay, so we have talked about this. This impedance is supposed to be greater than 50. This impedance is supposed to be greater than Z2. Okay, so Z1 is supposed to be greater than Z2, and 1000, that is your RS source resistor, is supposed to be greater than all of those. Okay, so it's like this. That's the story. And you continue this procedure for the entire, or if you want to cascade more sections. So you find for the first stage, you find the Q, you repeat the same procedure as we did for the double L matching section. Your high impedance is 1000, the low is 500, find the Q. Then find from the design equations, you find the parallel and the series reactive elements at 1.5 megahertz, that happens to be the design frequency. Find out the capacitor and the inductor values, okay, at those frequencies, design frequencies, same frequencies, L1, C1. Then for the second stage, since your high ZL1, which is the high impedance, is 500, low is 100, that is ZL2 for the second stage. Okay, this is the first stage, this is the second stage, then you have the third stage. Okay, and you find out the Q and then find the reactive elements. Do it for the third stage as well. The low one is your load resistor over here. The high is ZL1. This is your, it's supposed to be not ZL1, actually ZL2 over here. So this is 100. 100 is greater than 50. So that's how you find the Q. From the design equations, find the reactive elements at 1.5 megahertz. And what you end up in simulating this circuit is that the Q of a uh, 3L section matching network. This is in pink. Okay, so this corresponds to this pink curve over here. Sorry, and this is your first. The red one corresponds to the single L matching section. So this is for Q1L, quality factor of only one L section. This is the quality factor of double L network 2L. So Q3L is less than. So for three sections, the Q drops. It's less than twice L, which is less than the Q of one matching section, which means your bandwidth of match is increasing, so the Q is decreasing. Okay, as we are increasing the number of L sections, your Q is decreasing. Okay, so the bandwidth of match, you can see if you are going to cascade more stages, you are compromising the quality of the match, and you're increasing the bandwidth of the match. Okay, because more stages they are being uh, they are loading the first stage. Okay, so due to this loading, uh, your quality drops. The quality factor drops. Okay, so that's about if you are interested in designing um, a lower Q cascaded L network. That's the story. Okay, the cascaded L networks will produce are used to produce lower Q match, unlike pi and T networks that we have discussed before that produces a low produces a high Q or a low bandwidth match.